Hello, this is the paper presentation for week 1 for the class CS 6263, Introduction to Cyber Physical Systems Security of the Online Masters in Computer Science, Georgia Tech, Fall 2018, September 2nd, 2018. My name is Victor Velasquez. I'll be presenting the paper Exploiting a Thermal Side Channel for Power Attacks in Multi-Tenant Data Centers. The authors of this paper are Mohammed A. Islam from the University of California, Riverside, Xiaolei Ren, University of California, Riverside, Adam Weirman, California Institute of Technology, and the paper was originally presented at the Computer and Communications Society Conference in 2017, held from October 30th to November 3rd, 2017 in Dallas, Texas. First, I want to provide a summary of the paper. Now, this paper focuses on multi-tenant data centers, also known as co-location data centers. Now, with the advent and growth of cloud computing and the Internet of Things, there has been a great demand for multi-tenant data center, making it a high growth industry and increasing the demand for these type of services. Now, with the growth on this type of data centers, several challenges come to mind, and this paper focuses on the security risk brought in by the power design and power systems within the data center itself. Within this context, the paper states that power capacity of multi-tenant data centers is typically oversubscribed in order to increase revenue and utilization of the facility. Now, the main reason for that, or for this practice, is the capital investment in power equipment is quite large for any type of data center. However, in the multi-tenant data center or co-location data centers, the data center operators usually perform this practice in order to maximize the profits and maximize the utilization of the data center power resources. Now, this practice of oversubscribing the power capacity, and we say oversubscribing, imagine an overbooked flight. They basically subscribe more demand or more tenants than the capacity of the data center has been designed for. And this provides an opportunity for a malicious tenant to attack and disrupt the power infrastructure of the data center by timing the attacks to coincide with the peak aggregated demand of benign tenants. Now, what this means is that a malicious tenant can monitor the power demand or behavior of additional tenants or benign tenants, as the paper calls them, within the data center and create a pattern and identify a pattern that it can exploit to attack or disrupt the power infrastructure of the data center, causing an outage and effectively taking the data center out of service. In the paper, a thermal side channel has been identified and exists, which can be exploited by the attacker to gather reliable information about the benign tenant's power demand patterns by means of a Kalman filter applied to recirculated air temperature data. And the paper finally provides a series of countermeasures that can be used to mitigate or prevent this type of attack. Now, moving on to some background, multi-tenant data center capacity is typically oversubscribed to 120% of the design capacity. And this is a value that is used in the industry in general, and it's taken as a value basically to increase or add the capacity of the tenants, taking into account that the tenants' behavior or the services that the tenants are running in their servers do not necessarily coincide all the time. So even if the tenants' demand in total as a design demand in, is higher than the design capacity of the data center, in practice, that demand will not be aggregated or will not be present at the same time, meaning that there is an opportunity to have less than 100% coincidence in those loads. Now, the susceptibility of the different data center topologies in terms of redundancy will be different and will differ depending on each one of those topologies. So on the right, we have an illustration of a tier 4 data center with the 2N redundancy, meaning that is completely diversified, and the data center contains or has redundancy in both in the utility side, generators, UPSs, all the way to the power distribution units in the rack space. This diversity and redundancy provides the data center with increased resiliency against this type of occurrences and outages. However, this type of redundancy also impacts the capital costs incurred by the data center operator because it is the most expensive architecture that can be implemented in a data center. Now, as I mentioned before, the practice of oversubscribing the data center tenants, it's done for mostly economic reasons and for utilization purposes. Remember, the purpose of the data center operator in a multi-tenant data center is to maximize its profits and maximize the utilization of the power resources of the data center. Now, looking at the occurrence of an outage, we want to understand what is the cost of that occurrence and how those topologies from tier 1 to tier 4 data centers are impacted by the occurrence of an outage in the data center. The paper goes into detail in making some estimations about what will be the cost per square footage per minute. And the researchers have estimated that the cost of an outage for tier 1 data centers is 3.3 cents for tier 1, 10.73 cents for tier 2, 77 cents for tier 3, and 93 cents per square foot per minute for tier 4 data centers. And as you can see, the more complex and robust and redundant the power architecture of the data center, the higher would be the cost of an outage in that data center. And as reference, the paper provides that in 2016, data center outages on average cost $740,000 per occurrence. Information provided by the Ponemon Institute on their 2016 Cost of Data Center Outages report. Now, when we look at the threat model for this paper, the authors start describing who could be the attacker, or what would be the characteristics for the possible attacker. And within the context of the paper, the attacker in this case would be a legitimate tenant of the data center, uh, someone who could be a potential competitor, and definitely someone that would have a malicious intent to cause a loss to the data center operator, being financially as well as in the image or branding of that data center operator. Now, what can the attacker do based on the conditions that are being assumed or assumptions that are being made on this analysis? In this case, the analysis assumes that the attacker can install high-power servers in the data center facilities. It can increase the power demand on its servers by running CPU-intensive tasks, and it can conceal temperature sensors on its server inlets, meaning that it can measure the inlet temperature that goes into the server itself. And the attacker is assumed that can perform computational fluid dynamics analysis. Part of the assumptions that the authors make on the paper indicate that the attacker cannot hide destructive weapons in its servers, and it can't modify or alter off-the-shelf servers to add malicious power elements. For example, it is assumed in the analysis that the attacker cannot go out and buy an HP server and change the power supply on that server so that it can insert or generate a power outage by just putting a short circuit within the server. The reason for that being that the attacker would like to stay anonymous and undetected, and by doing that or taking an action such as a short circuit, it would be it would cause the circuit breakers on its own rack or server to trip, making it immediately identifiable. Now, what happens in reality is that not all of the cold air is utilized, and at the same time, not all of the hot air is captured by the air handling units. And what you have is some of that hot air will flow back into the cold air aisle through the common space at the top of the data center or the top of the rack space. Now, what the authors are proposing in this paper is that heat recirculation, as you see here, will impact the inlet temperature on some of the racks of the servers. And that temperature difference carries information about the power consumption and power demand from the benign data center tenants. Now, from the from the literature available and reports, 80% of data centers have at least 20% of their racks without heat containment, and 20% don't use it at all. Now, talking about heat containment, what it means is that data center operators can improve their efficiency and can improve the airflow of those cold air aisles by isolating and containing the airflow. Now, the resulting effect of that is that they minimize the heat recirculation by isolating the cold air aisles. Now, the authors developed a heat recirculation model in order to help them determine and describe the thermal side channel that the attacker can use to capture and de define and determine the information about the power demand patterns from the benign tenants in the data center. What the authors did was use a common filter, which is a classic tool to estimate hidden states from noisy observations. And what that means is this is a statistical model that removes or filters, as it says, noisy observations or measurements from the thermal side channel, meaning it can provide a more accurate measure of the temperature values as measured by the server inlets from the attacker side. Now, by applying the common filter, the attacker can determine the aggregate power demand of the 9 tenants with high accuracy. He is able to capture 54% of attack opportunities, meaning the attacker will be able to capture or be aware of those moments of 54% of those moments where the aggregate demand from the benign tenants are available for him to generate the attack. And what would be the attack strategy? The authors consider a simple strategy where the attacker keeps using its maximum power as contracted with the data center operator for a fixed amount of time, meaning that when the time is right and the attacker detects the right conditions to perform the attack, it will turn on or increase the power demand from its servers for a specific amount of time, and until the attack or until the um, outage condition is generated, and it will repeat this cycle using the model described on the illustration on the right, meaning the attacker servers will wait until the right conditions are met, meaning that the power estimation is higher than the power threshold. At that point, the attack, the time to wait expires and the attack commences. Now, the attack will be occurring for the time specified. When that time expires, then it will hold and it will start the cycle once again. Now, the authors describe this pattern and strategy as a measure to conceal the attacker's purposes and ensuring that the attacker is not detected. They argue that if the attacker is constantly operating at the maximum capacity or maximum demand that it has contracted by the or with the data center operator, it will incur impossible penalties and uh, ultimately might be even evicted from the data center for violating the data center policies or user agreement. Now, now that we know how the attacker can determine how to use the thermal side channel, what can we do or what can the data center operator do in order to mitigate or prevent this type of attack? And the main conclusion that the authors come to is to degrade the side channel, either by randomizing the supply air temperature, randomizing supply airflow, or by heat containment. Let's go through each one of these. Randomizing the supply air temperature means making variations in the air supply temperature. For example, on a typical data center, the data center temperature might be set to 60 degrees Fahrenheit. By randomizing the supply air temperature, the temperature set point will change at random intervals. It could increase to 65 degrees Fahrenheit, 70 degrees Fahrenheit at random intervals. Now, this puts a stress and re additional analysis requirements and additional computing requirements on the DC operators and the data center operators um, infrastructure, and might not be uh, economically viable. Now, the second option, randomizing air supply airflow, involves changing the openings of the vents in the data center raised floor so that the airflow, the amount of air that is pumped into the cold air aisles, is randomized or changes. Now, this is very similar to randomizing the air supply temperature, um, and has the same constraints. Now, the most effective way to degrade the thermal side channel will be to, to implement the heat containment by isolating the cold air aisle and eliminating or reducing significantly the hot air recirculation. By doing that, the thermal side channel all but disappears since there is no information carried on the temperature variances from the air's recirculation. Therefore, the attacker cannot know the power demand behavior from the benign tenants in the data center. Now, finally, the paper concludes that an oversubscribed multi-tenant data center is highly vulnerable to maliciously timed high power loads. Also, a thermal side channel was identified that contains information about benign tenant power usage, and a Kalman filter was designed to guide the attacker to time the attacks for creating power emergencies. And finally, the experiments showed that the attacker can capture 54% of all attack opportunities with 53% precision rate. With that, we conclude this presentation, and I will address any questions online. Thank you.